Hi class, it's Bill Berry back with the last, I promise, video on trees. They are tremendously interesting and it's taken us a little time to get through all of what they have to offer, but that's a worthwhile journey. So let us jump down and talk about our last topic, which is rebalancing and why that's so important. Remember that trees have this wonderful property in terms of searching and adding, and that is they keep not only search optimal, but if everything's right, adding is also very much in the same vein of a big O of log base 2 of n. It's a log n algorithm. As your data gets big, the searching and the adding of an individual node does not get big nearly as quickly. So if you have a tree, think about it, with 1,023 nodes or 1,024 nodes, it only takes you 10 searches, 10 compares to find the thing that you're looking for or to find that it doesn't exist. That's great, right? That's very, very fast. So we want to keep that optimal complexity, right? We like big O of log n. That's a sweet, sweet number. So we want to keep that. But what happens if the tree is not height balanced? Then it loses that property. In fact, it starts moving from log n to being a linear algorithm, which is big O parentheses n, right? Big O of n. So you can think about it. If you happen to get data in this format, if you happen to read the data and you just have an unfortunate set of data, you could end up with a tree that looks like this. It's a proper binary search tree and it'll work, but that ain't going to be log n, right? That's going to be n. So we don't really want that. So what happens? Because when you add data randomly to a tree, it's going to not always be height balanced. It's going to get lopsided at some point. So how do you know that you need to balance it, right? How do you know that? Then how do we rebalance it? What's the method or methods that you can use to do that? And then how often do we have to rebalance? Those are all interesting questions. We're only going to touch on it. We're not going to look at all the code because that certainly gets complicated. But I just want to tell you some of the options here, and then we will, we will sort of send you off to look up some of the interesting things if you want to look a little bit deeper. So the first is a periodic rebalance. This is the poor man's way to balance it, and that just says, look, from time to time, we're going to use a fairly crude method to rebalance the tree. Right? This is crude. It ain't pretty, but it'll work. What does it require? Well, create a sorted tree. You know how big your tree is. You probably keep a count. You know how big it is. Make an array that big. Do an in order traversal of your tree and fill in the array with all the data. So you have a sorted array made from your tree. Recursively then, find the center point. Right? Find the center point of the array, and if you're doing your math to split it, just be careful. If you're using integer math, then that's fine. Just remember, use the same integer math each time. If you're doing this by hand, it's easy to get off and do integer math one time and then rounding a different direction the other. So be consistent if you're doing this by hand. And then take that middle element and just toss it into the tree, right? Into a new tree. So make a new tree, toss in the middle element. Then recursively do the same thing with the left half, and then recursively do the same thing with the right half. And then each time recursively you're going to split what's left in half. You're going to take the middle element, then you're going to recursively call the left side of that and recursively the right. Notice that you don't need to touch the middle one. You've already thrown it in, right? So you can eliminate the middle one from consideration each time. And if you do that, you will end up with a new tree, and that tree will be height balanced, guaranteed, right? Absolutely guaranteed to be. So if you want to try that, I suggest that you do an example where you actually walk through, take a wonky tree. You can use the wonky one that's just above, and you'll see that what happens is we would pick 3. That would be the top of the new tree. Then we would recurse to the left, and we would do these, and then let's say maybe 1, because there's only 2 of them, so you got to go one way or another. Then we'd throw in the 1, then we'd throw in the 2, and on this side we would split it in half. We would throw in the 4, then we'd throw in the 5. If you think about that, that tree is going to be balanced, right? make a bigger tree than that though, right? Get some playing cards, get some, write some numbers, do something interesting, or write the code to do this, go find some code, or better yet, write the code, and you'll see that it does create a balanced tree, right? It ain't pretty. It's not a beautiful mechanism, and it's not one that you would do all the time. This is a very slow, very, it's a clunky algorithm. But it can be done, right? It's not horrible, it can be done. So you wouldn't necessarily want to do this after every add and delete. You'd want to find some reasonable period. So maybe this data is all written and read from file at a certain point or backed up at a certain point, or maybe there's some reasonable time in which you say, look, when X thing happens, we're just going to do a rebalance. Now, that's great, that's fine for us, but heavy-handed, right? If you really have a tree that you want to keep absolutely correct all the time, if you want to create, for instance, if you're using a tree to create an index for a database, which maybe you are, right? It's not an unpopular thing to see in a database. You might need it to be a little bit more clever than that. You might need to balance as you go, and if so, it requires some way different kinds of thinking. It requires some interesting rotation. The way that I think of it, and this is a crude approach, a crude thought, but think about it, and at least it gives you the idea. What if, let's think of these things as all sort of hanging on a little wire, like these are little coat hangers or something, little wires. If I could take the 3 and grab it by the top and just pull it up, and all of the rest would sort of fall back into place, do you see what would happen? The 3 would go up, and then the 1 and 2 would need to go to its right, and the 4 and 5 would fall to its left. Now, you still have to get those things in the proper spots, but the idea is you've rotated the tree and sort of pulled up one point to be the center and then fixed up the right and the left to work. That's a crude illustration, a crude analogy, but at least you get the idea of, yeah, you're sort of lifting the 3 to be the center point. So those are super cool. There is a scholarly paper on AVLs, right? Self-balancing tree, and the AV and the L are from the people who wrote the paper. Now, this is a tough to read paper. This is a true scholarly academic sort of paper, so read that if you like. Good luck with that. The other thing that's a more practical way to do it, and it's still a little mind-boggling at the beginning. It still takes some thought, but if you really want to understand more about continuous rebalancing, research red-black trees. The thing that happens with the red-black tree is that they add one more piece of data onto each node, and that is marking the node as either red or black. You want to know why it's red or black and what that means? Well, look it up, but it has to do with how many things can you alternate, or can you have things that are successively red or black, and is that a problem? So red-black trees are probably one of the most practical ways to understand and implement a continuous rebalance. So look those things up. There's some examples. There's certainly plenty of videos on the internet to see these in action, but these are cool, and look those up if you want to know more about continuous balance. If you go into some other programs, if you do more data structure courses in the future, you may well run into that, right? You may well run into red-black trees and implement the code for those. So what's left for us here? Well, really just to share some reference links. You are certainly capable of finding things on the internet, but in terms of references, here are some things that I have read that I thought were kind of interesting. So I'm sorry I can't share these links more easily here. I guess I could paste them in the comments or something, and maybe I should do that someday. But here are some links that, if you wish to take advantage of them or go search for them on the internet, you will find plenty to look for there. Last but not least, that brings us to the end. Really the end. That was a lot of videos on trees, but again, they're super interesting, and the code for them is super interesting, and they provide us a way to use recursion in a way that does make sense. Remember, it uses recursion in a smart way because most of our algorithms are dividing and conquering. They're dividing the problem in half. Therefore, our algorithms are log n, so they are not bad uses of the stack. They are, in fact, a pretty darn good use for recursion. So thanks for watching this video. video series. I hope you're finding it interesting and useful, and we will hope to see you back for another video. We still have several weeks to go in our course. There will certainly be more videos to go along with that material. Thanks again.